Alright, so this is a problem from an old EE310 midterm 2, and you are finding v of t for t greater than 0 using Laplace transforms and what we've learned about the S domain. So the first thing that we need to do for these types of problems is you have to solve for the initial conditions because they are necessary to represent the energy stored in the inductor and the capacitor. Okay, so let's do that. So t less than 0, let's redraw the circuit. Current source right there. The switch is initially open, so we don't have to draw that. Inductor here. 1 ohm resistor on the bottom, and the capacitor over here. Right, so this thing has been closed, or this thing has been open for a long time, and because of that we know that the inductor is shorted and the capacitor is opened. Right, and the initial conditions we are looking for are V of the capacitor, right, and I of the inductor. So this guy, right, there's a piece of wire right here. The voltage across a piece of wire is 0 volts. 0 volts. And so the current flowing through this guy, we said that the capacitor is open, so there is no current going this way, right? No current. So the only path for current is in this circuit, and it is flowing like this. And because this is a current source, we know that it is 2 amps. Right? So the current flowing through here is 2 amps. Cool. So these are our initial conditions, and we will need them later. But let's move on. And now the next step is to draw the circuit for time greater than 0. So there's our original circuit. And let's draw this thing for t greater than 0. Okay, so that goes here. Notice that the switch is now closed. It's our 2 ohm, the inductor, and the capacitor. Okay, so notice that this shorts out this portion of the circuit. Okay, we are looking for an equation that describes V over here. Right? Any current flowing through this guy is going to hit this piece of wire and all head this way and go back. Right? So none of the electricity over here will affect this V over here. So essentially, you can view this as gone. Right, because it is shorted out due to this wire. So now we're just left with this stuff. So this will be 2 ohms. Right, and we said that this is 1 Henry and 0.5 farads. Right, half a farad. So now this is time greater than 0, but we have to convert it to the S domain. AKA, we have to put this in terms of S and this in terms of S and account for the initial conditions. So let's redraw that. So there's the 2 ohm, the inductor, right? And then, as I said, we have to represent the initial conditions, right? There was energy stored in this thing previously, and we do that by plopping in a voltage source, right? Minus and plus on this side. If you really want to look up more on this stuff, we do this for an inductor and a capacitor. You can find it on page 49 in your book. If not this page, somewhere very close to this page in your book is what you want. But notice the polarity on this thing. For inductors, if the current was flowing this way, you have the minus on this side and the plus on this side. Okay? And the same thing happens for the capacitor. Plus, minus. Notice that the polarity is flipped for the capacitor, right? The voltage source for the capacitor, the plus side goes over here and the minus side goes over here. So let's get the values of these things. This is 2 ohms. Alright, so in terms of omega, we have J omega L. This will just be equal to S times L. Okay, so S basically just equals J omega. And that's it. It's just shorthand. So L is 1, so that'll just be 1 times S is just S. And this guy will equal L times I naught, or times I 0 minus. Alright, we said that this guy right here, this was 2 amps, and we said that L is just 1. So the value of this thing will be 2 volts. And notice, plus on this side, minus on this side. Okay. For a capacitor, we've got 1 over J omega C, and this will equal 1 over S C. And for our problem, we've got 1 over S times 1/2. And whenever you have a fraction on the bottom, you can just make the denominator go to the top. So this will equal 2 over S. Okay. So this is 2 over S. And the value of this guy, this is V 0 minus over C. Alright, but we said that this was equal to 0. Right? If we scroll back up, V of C equals 0. So this guy can technically go away. Okay, so this is the circuit, and now we can play with this. So let's just remember that V is right here. Now we can use this circuit to get an equation that describes V. So we're going to use Kirchhoff's current law, because it will give us only one equation. Right, and this branch right here, this will be V over 2. This branch right here, this will be plus V minus. Alright, so we're looking for the current flowing through this branch, right? That would be this voltage minus this voltage divided by this impedance, right, which is just S. So this voltage right here is defined because our ground is right here, right? So this is 0 volts, and then we said that we have this plus 2 volts right here. So if this is the positive side of the 2 volts and this is 0, that means to drop, this has to be negative 2 volts on the other side. Because if we were at negative 2 volts here and then you had a 2 volt rise, that would bring you to 0. So this spot right here, this is negative 2 volts. So V minus negative 2 divided by S. Okay, so and 2 negative signs just become a plus, and this is V plus 2 over S. Okay, so that describes this branch. And the last branch, we've got V over 2 over S. Okay, and like I said, if you have a fraction in the denominator down here can just plop up to the top. So this will really become v, we said s goes to the top, times s divided by 2. Right, and this whole term will have to equal to 0. Okay? So let's do a little bit of simplification and cleaning up. Let's say that this is v over 2 plus, this will be v over s plus 2 over s. Okay, all I did was break this down into two terms to make it look a little bit cleaner. Plus v times s over 2, and this still all equals 0. So now let's get rid of the fractions and multiply times 2s. Alright, so times 2s. So if we multiply times 2s to get rid of the 2's and the s's on the bottom, this term times this term, the 2's will cancel out and we'll get v times s, plus this term and this term, the s's will cancel out and we'll get 2v, plus this term and this term, the s's will cancel out and we'll get 4. And then this term and this term, the 2's will cancel out and we'll get plus v squared. And this will all equal 0. Alright, so once we get to this point, let's move this over here so that this will become -4. Right, subtract 4 from both sides. And then we're going to take out the v over here in the next step, right? So v times s squared plus s plus 2 will equal -4. Okay, and now we can just say v will equal -4 over s squared plus s plus 2. And boom, now we have an equation describing v. But this thing is still in the s domain. Or, yeah, it is in the s domain. So we need to turn this back into the time domain using what we know about Laplace transforms. So, let's copy this and paste. Okay, so now we're dealing with the problem of getting this back into the time domain. Right, so if you look at your Laplace tables, right, you have two tables. Alright, so you have two types of Laplace tables, right? You have the Laplace properties as well as the Laplace transforms. Okay, so for this, let's break this down and make the denominator a little bit easier to see. And this will be a common trick that you see a lot, is completing the square. Alright, so to complete the square, we will have s on the bottom, so plus, you take the constant in front of this term right here and divide that by 2. So the constant in front of the s is just 1. So 1 divided by 2. And you put parentheses around both of those guys, square that. And then that'll be plus 2. But you have to subtract this term from it still. Right? So this will be minus 1/2 squared is 1/4, right? 1/4, which really just equals, what is this? This is 8/4, so this will equal 7/4. Right, so plus, whoops, we said that it equaled 7/4, right? A lot of times you will see this broken down in terms of its square root squared, right? So what do I mean by that is rad 7/2, and then you'll see it written like this, squared. So that's what we're going to do, because it helps very much in terms of simplifying the Laplace, the inverse Laplace. Right, squared, and then all of that, the -4 is still on top. Right, so I know that from the property, or from the transforms, that sine of AT equals A over S squared plus A squared. Right, so this looks like a very good option because we have an S squared over here, right, S, and we have a constant squared, right, and some constant. The idea is we have this, except there is a constant in front of it. Constant. So this -4 is basically a constant times A. Okay, so, and then from the properties, whenever you have this, this is called time shifting in the S domain. Okay, so when you have an S plus something in the parentheses, it's going to correlate to an E to the negative whatever that constant is, right? In this case it's 1. T. Okay, so what we're looking at is we're going to have, change colors, we're going to have a final answer that looks like some constant times e to the negative, this term, 1/2 t times the sine of a t. Alright, we're going to have some answer like this, times u of t. Don't forget this, because you will get marked off. So let's see if we can make that happen. Scroll down just a little bit. So this would basically be e to the negative 1/2 t, we know that's correct, times sine a. So if it is in this form, this is a, right? So this would be rad 7/2 t u of t, and the only thing we need to figure out is the constant, right? This constant in front of here, because this is definitely not a. So what we're saying is -4 basically equals some constant times rad 7/2. Right, so we can say C will equal -4 times, when you're dividing by a fraction, you just multiply by the reciprocal, right? So this would be 2 over rad 7 this thing equals negative 8 over rad 7. Okay, so we can just plop that out in front. Negative 8 over rad 7. Alright, and this is our answer. So V equals this thing. And do not forget this. Okay, U of T, you will get marked off. Remember, because of the switch, right up here, because of the switch, we are starting this at time equal to 0. So that is what the step function, or that is what U of T does. Because the switch flips at time equal to 0, we need to start our function at time equal to 0. Right? And that is what U of T does. It says your function starts at time equal to 0. Okay, so don't forget this. And that's all I got for this video.